Thank you, Dana, that is the best foundation I got here. Before we actually talk about the security and the cryptographic, the actual implementations that we will be using in the automotive applications. And actually, thanks to Sarah to arranging in such a way that we got the process introduced, and then now we are going to talk about the actual cryptographic algorithms. And here my story for the day. I hope. Okay, that's fine. I will go with this. So my story here is to explain about what are the challenges that on a day-to-day basis, we face in the automotive applications, and how do we deal these use cases, so especially the use cases around the automotive and SDV, and what are the cryptographic algorithms that we recommend in those use cases. And also, one of the use case that the remote access, try to access your car using a digital key solution, and what are the security algorithms that we used over there. And the next point that I'm going to cover is what are the opportunities that we have in the Eclipse Foundation to build the kind of components, generic components or common libraries, in order to enable these cryptographic algorithms around, to enable the cryptographic algorithms in the security area. So in this slide, as Dana mentioned, I think a lot of process that we have around to build these SDV applications are the platform. Of course, we have certain audits, and which enables, we make sure that we build the automotive products in a secure way from requirements till the delivery. But the key important point that I would like to cover today is about how do we actually implement, how do we design these applications to talk to each other, and how do we implement them and deliver them, right? So, of course, my key focus today is about only the applications and the cryptographic algorithms that we use, that we used in our experience at Harman. And okay, so of course, security is the paramount, in the SDV, where even without being very near to in the proximity of the vehicle, users can try to attack the attackers can try to access the vehicle remotely and try to gain access to control various things. But these are the fundamental 4 areas that we come across, where the very first one is the communication. The communication means which includes the connectivity as well as the connected services, which will be trying to access the vehicle various channels. And the second point is authentication and authorization. How do we enable these authentication authorization in terms of application to application communication, as well as when one application in the vehicle trying to connect to some third parties or in the supply chain or even in the OEM systems, right? So if you look at in the connectivity, we have the standard channels like OBD, Bluetooth, Wi-Fi, cellular, of course, and also vehicle-to-vehicle communication. And also the connected services where we have the telematics, and diagnosis, supply chain, and of course, infotainment. Infotainment is also one of the big area where we could expect some threats. And the third point is about the OTA updates over the air. How do we update the software in the vehicle, and how do we make sure that the right software with the right integrity and the right the origin, the content is actually coming from the either OEM or from the supply chain or some third party. The right content is actually how we can bring into the vehicle. Of course, the last point, the last area in this is the data protection. Of course, we have tremendous data about the user, which includes some kind of some PI data as well as some kind of location data, or maybe very very personal data that how do we protect this from the other threats. So, and the risks include the man in middle, denial of service, and remote control access, of course the data theft and manipulation. So these are the risks that includes if it doesn't take care of the proper cryptography or encryption when we are talking the applications in the SDV area. Okay, so this slide is interesting, which covers how or what are what kind of attacks that we see, based on internal as well as public information. If you look at the telematics channel, which have the highest number of attacks, like 35 plus, whereas the next followed by the application services and followed by the infotainment systems. If we include these three itself, maybe more than 60% of threats that we could see here, and followed by the small amount of threats like from either ECUs or EV chargings or navigation systems, etc. The key focus today that how do we deal these at least 60 to 70% of threats, what type of algorithms that we need to use when we are designing these applications. And now the respective use cases that we are talking here. First of all, when we're talking about the communication means how do we enable the secure communication? How do we protect the data in transit, and how do we prevent the man in the middle, and also how we can prevent the tampering of the content communicating between the two parties, either vehicle, within the vehicle, application to application, or from a vehicle to any other channel that we just discussed. So the basic algorithms that we recommend here is the elliptic curve, RSA, as well as AES 256. We'll discuss about which use case exactly, how these algorithms can be enabled in the further slides. But here is just an introduction about these algorithms, and to provide the access control. We need to make sure that the user is verified before actually trying to access certain applications or certain devices. And how do we appropriately grant these accesses access to the vehicle features based on certain authentication and authorization protocols. For example, ECDH is the right one, and of course the SPAKE2, which is kind of fundamentally very stronger than the other algorithms in the especially vehicle and the low powered ECUs that we use in the vehicle. The next point is about the secure updates, where how the content will be actually delivered, and how do we make sure the integrity of that content, and how do we make sure make sure any of the malicious content is not reached to the vehicle, and how do we enable that is by using this SHA-256 and ECDSA. Of course, these are the algorithms that we are talking. We will be seeing further details in the next slides. But you just note that these are the algorithms that we recommend to use in this situation. The last one is the data privacy, where we would like to enable the encryption for the stored data, either it is in the vehicle or in the cloud or wherever we wanted to secure the data to avoid the theft. We would like to encourage to use AES 256. Okay, now see, these are the algorithms that we just discussed. They're not new to the industry. I mean, they were there since, like, I think, if you look at maybe Diffie-Hellman algorithm or elliptic curve, like these are there since 76, 77 onwards. But why we are talking about these now? How these will help us to build these security in the automotive applications. So if you look at the first challenge, of course, nowadays, we could see like hundreds of thousands of ECUs that we are using in the vehicle, and each ECU or each the processing unit may not be equipped with full-fledged cryptographic algorithm that it can process. That means we have actually very low-end IoT devices or ECUs that we might need to use in some cases. In that case, we cannot go with very complex algorithm like RSA, because it needs a lot of computational resources to be used. And that's where we would like to encourage to use the elliptic curve. We'll talk about this curve 25519, which is not patented yet. But in the case of elliptic curve, there are lots of patents, and we are not open to use all the patients because all the curves because of its patented. And the key management, especially on the cloud, there are lots of solutions that are already available to manage the keys. But in the vehicle, if you wanted to manage the keys and make sure that how we generate the keys and how we actually rotate the keys and how we actually distribute the keys different applications in the vehicle, the key management is very, very critical. And that's where we would like to have some kind of HSM enabled libraries or some platform components so that they can actually and help us, all the applications, to use, to generate the keys as well as rotation and other requirements in the key distribution area. Of course, we have seen this OTA updates, but how do we actually enable that the software that we wanted to that we have built, and we wanted to bring that to the vehicle and then make sure that we install that with an integrity by enabling the digital signatures. And of course, the elliptic curve digital signature is the algorithm that we would like to encourage you to use. And interoperability and the legacy systems. This problem is sometimes we need to run the legacy systems or the legacy equipment along with the new things. And that's where we would like to bring in wherever we need. For example, if you are trying to access the vehicle using your high-end mobile, but when the same mobile is communicating with maybe in the OEM cloud or something, then the kind of algorithms or kind of cryptography that we use when mobile to the OEM is different to the mobile to the vehicle, because the vehicle may not be that equipped. So that means even it is in the other order, in the other way also. For example, if your vehicle have some kind of zonal architecture where one of the zone is equipped with high-end ECU, and if it is talking with the cloud or the other high-end ECU, then it can use high computational or high cryptographic algorithms. But if it is talking with a small ECU within the vehicle, you will not be having that liberty to use the similar algorithms. So that's where we would like to use, cautiously, what type of algorithms in which situations. Last one about the supply chain. The supply chain have, as we just saw in the threat analysis, the supply chain is one of the key area where the vulnerable components that can come from the supply chain and then might impact the other components within the vehicle. And we would like to make sure these are coming from the trusted source by maybe a mutual TLS or enabling some sort of identity providers, which will help in order to pull the content from the third party or supply chain and make sure that we actually process that in the vehicle without any anomalies. With this, I would like to introduce an algorithm called, of course, we definitely heard this since a long time. But what is going to help us is to enable the first situation, like in the communication, to enable the encryption, we might need to go with two different algorithms, which is symmetric and asymmetric. In case of symmetric algorithm, we will be using the same key at source and the destination. That means the source and, both the parties are using the same key to encrypt and the decrypt. But the flow with this is like, the flow with this is the key is known to the other party, and we cannot guarantee that how if it is a known trusted party, then it is fine. But if the other party is some third party, and we cannot control how they will be using the keys, then definitely this symmetric key is not the right solution. Then we must go for the asymmetric keys. That's where we should be using like RSA or ECC. So in case of RSA, we all know how the one party can generate a public key and the private key. And when it is sending the content to the other side, it will be using its private key to encrypt it, so that when the content went to the other side, the other party will use the public key of the public key of the first part, and then try to decrypt it, so that they know they will be able to communicate each other without any third party involvement. And the only drawback with this is the RSA algorithm is, as I just mentioned in the previous slides, it needs a lot of computational resource. But if we go with the next algorithm, which is the elliptic curve cryptography, so the elliptic curve is actually formed based out of some mathematical equation, some sort of a mathematical formula. Based on that, we will be drawing a curve in x and y axis, and when we are actually the number of rotations that we follow on the curve, depending on these mathematical computation, it is very, very difficult to find out what is the private key. In case of RSA, it is of course difficult, because I think a couple of weeks back only I heard someone try to crack a 50-bit encryption key using some quantum computers, or by hiring some 2K per hour, and they will be able to crack 51-bit key RSA algorithm. But in this case, if you compare the ECC and the RSA, the same strength that we will be getting with the 256-bit in the ECC, which needs 3072-bit in the RSA. Similarly, 384 and 7680, these are the key lengths that I'm talking about here. So that means with the less computational resources, we are able to reach the same strength of RSA in ECC. So that means if you have a low-end device or a low-end ECU in the vehicle, and if you want to run some kind of application in that, and if you wanted to enable an encryption, if you want to enable some kind of security in the low-end ECUs, then the EC or elliptic curve algorithm is the best algorithm to enable the encryption in the communication. And of course, the next one is the authentication and access control. So the use case is where we cannot run any, or we cannot use any traditional authentication algorithms, or this public key, private key kind of stuff may not be possible in some situations. For example, if you wanted to enable some remote commands over a small device, and that small device, maybe user will not be user will not be able to get this public key, private key when they are running these applications. So that's where we would encourage to use the SPAKE2 algorithm, which is based out of the ECDH. ECDH is again the DH is the Diffie-Hellman algorithm, which is very, very a simple and a strong algorithm. Here, for example, like, you will be having a common numbers like P and G without sharing the private key of each other. That means, like, party one will have their own private key, and party two their own secret key. But without sharing these to each other, they will still share some common key calculated based out of these two generated numbers like P and G. And they actually share that key, even though with sharing that key, they will not be, the middleman will not be able to crack, like, what is the private key that is used by the two parties. So with this approach, in the SPAKE2, there is additional check that will be added by by using the prover and verifier algorithm by one more round. So that will make sure that you will not be able to crack these type of algorithms, these type of keys using SPAKE2. And of course, the SPAKE2 needs only the PK infrastructure, which is critical for the authenticating vehicles in the software, and firmware, as well as meaning secure communication between entities. And the next one is about auto updates. So as I was mentioning, like, SHA algorithm is the suitable one, because we do take the hash of the content that we wanted to push to the vehicle, and then we will make sure that applying the same algorithm and make sure that the same hash has been checked. And that means that, it will make sure that the content is not tampered. It is received as is, as well as we use the digital signatures to make sure that the content is coming from the original author, whoever provided. So that with these algorithms, we will be able to successfully achieve these over-the-air updates in a secure way. Of course, the future is much more complex, as I just mentioned about, someone try to crack an RSA algorithm. But that means, like, in near future, they can even crack, even if you try to use 512-bit or even 1024-bit algorithms. So that means, like, we need to be prepared well, that what type of algorithms and what is the strength that we need to use, depending on the new algorithms that are coming to crack these keys. And we need to make sure that we will be using these post quantum cryptography algorithms. Of course, these are still in the research stage, and there's no standards available in the market. But we need to keep an eye, like, how this is behaving, and based on that, how we need to adapt to those algorithms. Okay. So, as I mentioned in my story, the digital key is one of the solution which is defined by the CCC. And of course, this entire flow is defined by as well CCC, which is open. And the solution includes here is how we enabled the communication between the vehicle and the device that you wanted to operate remotely to the vehicle. You want to operate the vehicle remotely, which can be a mobile, which can be some tablet, or any sort of device that will be here. And here is the vehicle. And as a OEM server, how do we make sure that we trust these mobile users, and the mobiles will operate this vehicle remotely, and how do we enable this security between this mobile and the vehicle and the cloud? So if you look at the very first algorithm, very first step, where the OEM is going to establish a secure communication between the vehicle and the OEM server by using this ECC, the elliptic curve algorithm that we just mentioned, or we just talked about. Because in the vehicle, not always we'll be using the high-end ECUs, and that's where we try to achieve that by using this ECC in the flow 1. But in flow 2, where the mobile is communicating with the vehicle by any of these NFC channels, like it can be Bluetooth, or it can be maybe USB, or it can be any other, maybe Wi-Fi, or for that matter. So that's where we have enabled the SPAKE2 algorithm in step 3, 4, 11, and 12. So with this, without any much resources, we are able to achieve the same security between the mobile and the vehicle. And of course, in the whole solution, we also have a friend device where you can actually pass the keys temporarily, or and assign him to access your vehicle for some time. And even in those flows, also the similar algorithms has been used. And to enable this, the OEM server to the mobile, of course, we need to communicate with the device OEM server as well. And that's where we have used the RSA, because those are like kind of cloud-to-cloud communications, and they are capable of the higher computational resources. So this is about the story. And now I'm coming to the opportunities that we need to build in the security area. So first of all, we need to have some kind of authentication and authorization server in the onboard as well as offboard. So that means offboard we have lots of already the IDAM servers that are available, and they are capable of communicating, authenticating the users in multiple ways. But if you wanted to have the similar security for the authentication authorization in the vehicle, and we need to come up with similar kind of IDAM, but it will be very lightweight, and then capable to allow the vehicle users and the vehicle applications to communicate each other. And the next one is about the key management solution. Of course, we have to build a tool or a library which can generate, rotate, revocation, and distribution that will abstract the entire key generation from the applications. For example, if any application wanted to generate a key that can start using this component or library. For example, we have this Eclipse Heimin, which is in the Eclipse Foundation, that do support a lot of such algorithms and some encryption standards. And it's an opportunity to enrich that with some of these SPAKE2 algorithms as well. The next one is about the remote operations, and how do we enable security and integrity of remote commands. So for example, that means that when you are sending a remote command from your device to the vehicle, and how do we make sure that the integrity is being taken care by the vehicle side, and how do we believe that this is the command that came from my trusted source, my trusted devices. So we need to come up with some abstract layer which can make sure that it will first check the identity of the command, the sender who is the right user, and then it will also check the access, whether it is allowed or not, and in which situations. For example, vehicle is in parking mode, or vehicle is in running mode. What type of commands that are allowed, what type of commands that can be completely avoided, or even when you are actually maybe when the vehicle is in moving stage, and is your application allowed to show some pop-ups that will distract the user? These type of things we need to take care from the Eclipse. This framework that we need to build to abstract these complex scenarios, right? And the last point is about we need to have kind of monitoring system that will enable end-to-end near real-time vehicle events. Not only the vehicle events. For example, this monitoring system should provide some kind of vehicle assets to management, as well as these allow to or understand all these vehicle events from the onboard as well as offboard. And then we need to build some kind of AI modeling around this SDV space, and understand how this can lead to some threats. And then make sure that we need to integrate with some kind of notification center, so that it can notify the users as well as the OEMs with the right information. So this is about the opportunities that I was talking about, where we can bring in the Eclipse Foundation with all these solutions. Of course, some of them we are already actively working on, and some of them we are yet to pick up. Okay, maybe that could be a quick one with, as a great foundation, I got it from the previous, Dana and Sarah, but with this, I would like to take any questions if you have.
Yeah, thanks, Satyam, for giving the overview and also call to action or some suggestions what Eclipse could provide. Any questions from the audience already? Ah, okay. I thought all of you are so secure that you don't see any issues.
Thank you very much, Peter Briller from AVL. About the suggestions on the last slide you just showed, I would be interested about what you think. Would you have some suggestions, a little bit more details about this last point, the real-time monitoring in the vehicle? Especially you're suggesting ML modeling for threat analysis. Is this something going on locally in the vehicle, or what would be your suggestion?
Yeah. So see. The building AI modeling for the SDV space means it should be able to understand what the automotive, the knowledge around. That means how the vehicle is moving and what events that are coming up, whether these events are threats to this. For example, you just applied some brake. When you are actually going in a proper normal road, and you already have some context that there are no objects surrounding. That means this can be some kind of threat, and that means we need to build this AI modeling to understand these certain use cases, and based on that, whether it is really an incident or it is something like normal behavior. Maybe like every vehicle that is going on that particular road is having the similar experience. Based on the context that we need to understand all these things, and then alert to the users and the OEMs.
Okay, so it's a kind of anomaly detection you're suggesting?
Kind of anomaly detections, of course.
Okay,
the threat detections.
I just have a question concerning the Tara analysis. So how to get this considered in combination with the SDV stack and SDV software?
SDV stack and SDV?
SDV software in general, because the Tara analysis is usually done on device level, so far I know. And now if we are talking about an SDV ecosystem, so how we consider this?
Okay. So actually, the Tara is still one of the best practice that we follow. When we are trying to build the automotive systems, during Tara itself, you can identify these are the different use cases and the recommended algorithms, or if they are already following. Otherwise, you can come up with the list of cryptographic algorithms based on the Tara analysis that you have. And the Tara analysis, yes, definitely it will continue as is. Even I'm not sure whether it is different for the SDV or normal automotive products.
And what do you propose to follow here? So top-down approach or a down-up approach?
That will be depending on the situation. For example, if you are working on a fresh solution where you need to understand the entire ecosystem, and that means maybe the top-down could be a better approach. But if you are trying to change as a CR in the existing systems, then we might need to come up with the bottom-up approach, and it depending on the situation.
Okay, thank you very much. I think here, so there is also a need to define a proceeding, so how this kind of analysis can be done in this new situation and in regard of the new SDV.
Sure, thank you. I'll definitely take this. Especially, not to deviate, but see, I'm from the architecture and the development background, and we have a separate security team that they will take care of all the processes that either Tara or even whatever the new process that we are talking. The security team will be working. But from the developer side, like when I'm designing some application, and how to enable that application depending on my situation. So that's where I am trying to cover here.
Yes. And do you intend to initiate a project here in the Eclipse?
Yes, yes. We already have, some of them are in the pipeline, and that will be coming soon in a couple of weeks.
Because this is also an interesting area for us, so maybe we can discuss this later.
Yes, yes, sure. I'll be around.
Thanks very much for the presentation.
Thank you for the, great questions.
Yeah, thank you. So I just actually wanted to follow up on that question. So does it mean all of around these 4 topics you are going to propose?
Yeah, as I said,
certain
not
projects?
all, but at least some of them we already, actively working on. But some of them we need to, to pick up.
Okay. So I think that's also, if somebody's interested then in participating and contributing,
that would be great.
You're quite open then for that. Yeah.
That would be great.
Thank you so much for this insight into security. I think safety and security needs to go hand in hand. Otherwise, we'll have some issues. So thank you.
Okay. Thank you all. Thank you.